All right, get ready, because today we're going deep, really deep into particle physics. We're talking about Peter Higgs's 1964 letter, a pretty important one, you could say, that explains how certain particles gain mass.
Yeah, it's foundational stuff, really.
I mean, mass, that's like pretty basic,
You
right?
think so, but it gets super complicated because it all comes down to this thing called broken symmetries.
Broken symmetries, okay, I'm intrigued already.
Well, what's really cool is that Higgs was trying to solve a big problem physicists were facing at the time. They were working with Goldstone's theorem, which seemed to say that in certain cases, you'd always end up with massless particles.
But we know that's not true, right?
Exactly. We look around and tons of particles have mass, so there was this mismatch between the theory and reality.
So it was like a cosmic puzzle.
Pretty much. And that's where Higgs comes in, like a genius detective. He basically said, hold on, what if we add something called gauge fields to the mix? And that's when things get really wild.
Okay, stop right there for a sec. For those of us who don't have a PhD in particle physics, what exactly is a gauge field?
Think of them like messengers. They carry forces between particles. So just like we have photons carrying the electromagnetic force, the one responsible for light and magnets, we have other gauge fields carrying other fundamental forces controlling how particles interact with each other.
Okay, so Higgs brings these force-carrying fields into the picture. What happens next?
He realized that when these gauge fields, these messengers, interact with something called conserved currents, something amazing happens. Some of the particles that carry these forces, the gauge bosons, they can gain mass.
Wait, so the interaction itself is what gives rise to mass?
Yeah, it's kind of mind-blowing, right? Think of it like this. Imagine you have a superconductor, like a special material, with a bunch of electrons all moving together perfectly. Now, introduce a charge to this system, suddenly you get these collective excitations called plasmons. And unlike the stuff in a regular neutral gas, these plasmons have mass.
Okay, I think I'm starting to see the analogy here. So Higgs basically found a way to show how massless particles could become massive, all thanks to interacting with these gauge fields.
Exactly. And to show this, he built a model with scalar fields and a vector field, all interacting based on this equation, a Lagrangian density. Imagine it like a recipe, but instead of food, it tells you how these fields combine and make all the physics of the universe.
We've got the recipe, but how does the mass actually appear? What's the secret ingredient?
Let's look at Higgs's equations. At first, he's got massless scalar and vector bosons. But then he introduces this coupling with the gauge field represented by the constant E. And when he does that, boom, the equations change completely and you get these terms that mean mass specifically for certain particles.
So E is like the magic ingredient.
You could say that. And here's why it's so important. If E is 0, meaning there's no interaction with the gauge field, we're back to Goldstone's theorem, all those particles are massless. But with that coupling, things become way more interesting.
This is where I get really excited. So it's not just a theory. This whole mechanism applies to real-world stuff too, right?
Oh, absolutely. One of the coolest things about Higgs's model is you can expand it to way more complex systems, like ones with SU3 symmetry, which is key for understanding the strong force holding atomic nuclei together.
We're talking about the forces that literally shape the universe now.
We are. And there's one more thing. Higgs' theory predicts what he called incomplete multiplets, meaning you won't always get a full set of scalar and vector bosons. Some are just missing.
Incomplete. That sounds like a disaster waiting to happen, or at least a bunch of confused physicists. What does that mean, like, practically?
It means there might be particles out there that we haven't discovered yet, particles that belong to these incomplete sets. Certain types of mesons, maybe like the K meson or the atommeson, could be some of these missing pieces.
So incomplete multiplets, they're like clues, hints that there's more to the universe than we know now.
Yeah.
Like missing puzzle pieces.
Precisely. And the exciting part is we're always finding new pieces of this puzzle. New particles keep popping up, and each discovery brings us closer to understanding how it all fits together.
It makes you wonder, what other mysteries are still hidden out there? What other incomplete multiplets are waiting to be found? And what could they tell us about the universe?
That's the amazing thing about science. There's always more to learn, more to explore, and Higgs' work has opened up a whole new path for us to follow.
It's pretty incredible to think this all started with a simple question. How do particles get their mass? And decades later, we're still wrestling with the implications of that question and the answers that Higgs gave us.
It just shows you the power of human curiosity, this constant drive to figure out how the universe works.
Well, on that note, let's take a quick break and come back to dive even deeper into the amazing world of broken symmetries.
And it's really changed how we think about the universe.
It's wild to think that one letter from 1964 could be so groundbreaking.
Well, Higgs' work was a huge piece of the puzzle, for sure. There were others working on similar stuff like Englert and Brout around the same time, but Higgs' approach was really elegant, insightful.
I'm curious, when Higgs was coming up with these ideas, did he have specific particles in mind? Was he thinking, this is how the W and Z bosons get their mass?
That's a great question. His first work was more simplified, but later on he started looking at more complex situations. He really dug into how his mechanism would work with a semi-simple group like SU3, which is really important for the strong force.
So he was already making connections to the real world of particle physics.
Oh, definitely. And remember those incomplete multiplets we talked about? Well, in his paper on gauge boson masses, Higgs specifically talked about applying his theory to a model where the scalar fields form an octet under SU3.
An octet under SU3, that sounds familiar. Isn't that how particles are organized in the standard model?
You got it. The SU3 group is super important for understanding the strong force, one of the 4 fundamental forces. It describes how quarks, the tiny things inside protons and neutrons, interact with each other.
So Higgs was connecting his ideas to the fundamental forces of nature.
Exactly. And in this SU3 model, Higgs found that you could have 2 non-vanishing vacuum expectation values, which could be chosen to be the 2 Y0, I3 members of the octet.
Y0, I30, though, those are quantum numbers, right? I kind of remember those from physics class, but what do they actually mean again?
Of course, quantum numbers are like labels that describe specific properties of a particle, like hypercharge, which is Y, and isospin, which is I. They help us classify particles in the standard model.
So basically, Higgs was showing how his mechanism could explain why certain particles with specific quantum numbers get mass, while others don't.
Precisely. And this leads to some really cool predictions. For example, Higgs thought there would be 2 massive scalar bosons with the quantum numbers Y0 at I and I3.
2 brand new particles with very specific properties. That's exciting.
It is. And on top of that, he predicted that 6 components of the scalar octet would combine with 6 matching components of the gauge field octet to form
Massive vector bosons.
Yeah.
The ones that carry the weak force, the one responsible for radioactive decay.
Exactly. And what's even cooler, Higgs predicted specific configurations for these vector bosons.
Like what?
He predicted 2 I12 vector doublets, which would be degenerate in mass between F plus 1, but have an electromagnetic mass splitting between I3 plus 12 and I3 12.
Okay, I might need a little help with that one. What does all that mean in simpler terms?
Imagine you have 2 sets of twins. Each pair has a total isospin of 12. These pairs would have the same mass, except for a tiny difference due to electromagnetic interactions. Like each set of twins is identical in mass, but one twin might weigh slightly more than the other because of, say, what they eat.
Okay, I can picture that. So 2 sets of twins, each with their own isospin and a small mass difference within each set. And these are all vector bosons, the carriers of the weak force.
You got it. And then there's also the I3 plus 1 and I3 the 1 components of a V0 I equals 1 triplet.
Another triplet, so 3 more particles.
Yep, and this triplet has a total isospin I of 1 and a hypercharge V of 0. The mass of this triplet would be entirely due to electromagnetic interactions.
This is getting pretty complex.
Yeah.
But it's amazing how Higgs could predict all these specific configurations based on his theory of broken symmetries.
And it gets even better. Higgs also said that in this SU3 model, 2 of the gauge fields would stay massless.
Not everything is affected by the symmetry breaking that.
Right, and these 2 fields stay massless because they're connected to the leftover unbroken symmetry under the abelian group generated by hypercharge, Y, and isospin I.
So there's still a bit of symmetry even after all this breaking. It's like a balance between order and chaos.
That's a great way to think about it. And Higgs even suggested that if another mechanism breaks hypercharge conservation, maybe related to the weak interactions, one of those massless gauge fields would get mass, leaving only one truly massless vector particle, the photon.
The photon. The particle of light. So he's saying even the photon's properties could be explained by this whole broken symmetry idea.
It's a pretty amazing possibility. And remember, this all comes from that one key concept: coupling conserved currents with gauge fields can give certain particles mass.
This whole broken symmetry thing feels like a fundamental principle of the universe, something that shapes reality itself.
It really does, doesn't it? And it shows how powerful these abstract theoretical ideas can be in explaining the world around us.
Okay, so we've covered how Higgs' mechanism gives mass to some gauge bosons and how it connects to the strong force. But he also mentioned these incomplete multiplets. What's the big deal with those?
Well, what's really interesting about incomplete multiplets is that they give us a way to test Higgs' mechanism. If we actually find these incomplete sets of particles out there in the universe, it would be pretty strong evidence for his theory.
So we should be looking for these incomplete multiplets.
Exactly. And it's not just about finding new particles, it's about figuring out the connections between them, how their properties relate to the underlying symmetries of the universe. Like, if we could find particles that fit the patterns predicted by these incomplete multiplets, we'd understand so much more about the forces that govern them.
It's like a giant puzzle, right? Each incomplete multiplet is a missing piece, and finding those pieces helps us see the complete picture of the universe at its most basic level.
Yeah, that's a great way to put it. And what's really cool is we're constantly finding new pieces, we're discovering new particles all the time, and with each discovery, we understand a little bit more about how it all fits together.
It makes you wonder, what else is out there? What other incomplete multiplets are waiting to be found? And what will they tell us about the universe?
That's the beauty of science, right? There's always something new to learn, something new to explore, and Higgs' work has opened up a whole new world for us.
It's mind-blowing to think this all started with one simple question. How do particles get their mass? And decades later, we're still trying to understand the implications of that question and the answers Higgs gave us.
It's a real testament to the power of curiosity and the human desire to understand the universe.
Well, I think that's a perfect place to wrap up our deep dive into broken symmetries and the incredible work of Peter Higgs. It's been a wild ride exploring how this seemingly abstract concept has reshaped our understanding of the fundamental forces and particles that make up everything around us.
It really has. And who knows what other mysteries are still out there waiting to be uncovered.
To all our listeners, keep those brains buzzing, and we'll catch you on the next deep dive.